today's video, we talk about two concepts. One is the heat of formation, which is a special standardized heat or enthalpy change that's tabulated in books and tables and websites, and a concept called Hess's law that makes use of the fact that for state functions, the pathway does not matter, that allows us to find some thermochemical characteristics of reactions that would maybe otherwise be harder to do, or maybe impossible. So first of all, let's talk about standard heat of formation. The standard heat of formation is symbolized by delta, so that's change, in enthalpy, H, and then the little degree sign means it's standard under standard conditions. So standard conditions, remember, means 25 degrees C, 1 atmosphere. Any solutions involved are at 1 mole per liter. And the little F stands for formation. So if this is an enthalpy change that's associated with forming a compound. How much of it? 1 mole. So you're making 1 mole of a substance. You're making it from the elements that compose it. Like for water, that'd be hydrogen and oxygen, for example. And those elements are in their most stable standard states. So their state, when they are at standard conditions, 25 degrees C and 1 atmosphere, whether that's solid, liquid, or gas, however they exist in their most stable state under those conditions, that's the starting point. That's the reactants in the formation reaction. And it's formed under standard conditions. So if we look at an example of this thermochemical equation, this delta H value is not an example of a standard heat of formation. And the reason for that is because we are making 2 moles, not 1 mole. This is also not a standard heat of formation. And the reason for that is because nitrogen is a gas at room temperature, at standard conditions. And here we're forming this from a liquid. This is a standard heat of formation because this is for a reaction where we're producing 1 mole of ammonia from nitrogen and hydrogen in their standard states. Now notice that quite often to be able to produce that product with a 1 mole coefficient out in front, you have to use fractional coefficients on the elements that make it up, particularly if they're diatomic, like nitrogen and hydrogen are. Okay, so our second topic is Hess's law. Hess's law says if a process can be described as a sum of processes, so you can add 2 processes together, the change in state for the overall process is the sum of the changes in state for the individual process steps. So this goes back to the definition of what a state function is. State function doesn't matter how you got from beginning to end. The change in that state function is still the same. Like latitude and longitude, it does not matter which road you took to get between those 2 positions. The starting and ending point are the same. So for example, if you have a process where A becomes B, and the delta H for that process, let's call that delta HAB, and then you have another process where B becomes C, and that has a delta H associated with it, if you could add those together, you would have A directly becoming C. And delta H for that process, that's going to be the sum of the delta H's for the 2 steps that we added together to make that final A becomes C. That's Hess's law. Let's do an example. Let's take this to a place where there's more space to work and work this out. Okay, so the objective here is to use these 2 reactions and add the thermochemical equations together to get the target thermochemical equation that we want here. Let's keep in mind that the heat of vaporization here for water, that goes with H2O liquid becoming H2O gas. So that's the delta H for that process. Okay, so when I'm doing these kinds of reactions, I want to make sure that the main reactants and products end up on the right side of the reaction, the correct side of the reaction, I should say. So I want C2H4 to be on the reactant side, so I'll take this equation and write it just as it is. So C2H4 gas plus 3O2 gas makes 2 CO2 gas plus 2 H2O gas. And delta H for that process is given to us as minus 144.1 kilojoules. Now I want C2H5OH to end up on the product side. So I'm going to take this reaction and I'm going to flip it end for end. So I'll do that. 2 CO2 gas plus 3H2O liquid makes C2H5OH liquid plus 3O2 gas. Delta H for this process is going to be the negative of the delta H that I was given because I switched it around. I reversed it. So it's positive 1367.1 kilojoules. Now if I look at where I'm at right now, I have 3 O2s canceling out, gaseous O2s. 2 CO2 cancels out. And I can't cancel the water out. Can't cancel any water out because this is water that's in the vapor state. It's the gas. And this is liquid water. So what I want to have in the overall reaction is I want to have 1 mole of gaseous water on the left-hand side. So what I'm going to do is put 3 moles of H2O in the liquid state on the right-hand side of the arrow so it will cancel with these 3 moles. And I'm going to put 3 moles of H2O gas on the left-hand side. Now, the process that I have my delta H for is the reverse of this. So the delta H for the process that I just wrote down is going to be negative 40.65 kilojoules. But that's kilojoules per mole, so I'm going to have to multiply it by 3 because I multiplied the coefficients by 3. So now my 3 moles of water liquid will cancel from both sides, and 2 moles of gaseous water will cancel from both sides. And if I add this up now, I have C2H4 gas plus everything's canceled except for my 1 mole of H2O gas. And then on the right-hand side, everything's canceled except for my 1 mole of C2H5OH. So delta H for this process is going to be the sum of negative 144.1 plus 1367.1 plus 3 times negative 40.65. And if I add that all up, I come out to 1101 kilojoules. So that makes use of Hess's law to find the delta H for a reaction that we didn't have to actually do in a calorimeter. One of the common uses of Hess's law is with the heats of formation that we talked about earlier. Here's how this works. Say we have 2 compounds, X and Y, and they are made of the same constituent elements. If we wanted to find out what the heat of reaction was for X becoming Y, we could do it in 2 steps because Hess's law allows for that. So we could take compound X and divide it into its elements in their most stable standard states, and the delta H for that reaction would be the opposite of the heat of formation because decomposing a mole of element X into its components would be the literal opposite of forming it from its component elements. Then if we took those same elements and reassembled them into compound Y, the enthalpy change for that reaction would be delta H of formation for Y. So if we add these together, the constituent elements are going to cancel out, and we just have X becomes Y. That's the reaction that we're interested in. What's delta H for this process? Well, it's the sum of the 2 delta H's for the individual steps, which turns out to be delta H of formation of Y, the product, minus delta H of formation of X, which was the reactant. So in general, we could say the delta H for any reaction is equal to the sum of the enthalpies of formation of the products multiplied by their coefficients, and that's where this N comes in, because remember, these are all going to be reported on a per mole basis, so we have to multiply by the number of moles that are indicated by the coefficient in the balanced chemical reaction. So you do that for products, and then you subtract the same quantity for reactants, this enthalpies of formation for reactants multiplied by their coefficients. So let's do an example problem. In order to do this, you're going to have to look up heats of formation from tables. They're available all over the place. You can search for them with a simple Google search or find tables online or in books, including your textbook. So to get delta H here, what we're going to do is we're going to take the sum of enthalpies of formation of products minus the sum of enthalpies of formation of reactants. So we have 3 moles of calcium sulfate, CaSO4. If we look up the heat of formation, it's negative 1434.5 kilojoules per mole. And then we have 2 moles of phosphoric acid, H3PO4. Its heat of formation is negative 1266.9 kilojoules per mole. So that takes care of our sum of heats of formation of products. Now we're going to subtract from that the same sum but for reactants. So we have 1 mole of Ca3PO42, calcium phosphate. Heat of formation for that substance is negative 4,121 kilojoules per mole. And then we have 3 moles of sulfuric acid, H2SO4. Heat of formation for that is negative 813.99 kilojoules per mole. When we do the math here, we get 8333 kilojoules. So that's the heat of reaction for that overall reaction. Let's try another one. The balanced chemical equation here is going to be 2NH3 plus 3O2 plus 2CH4 makes 2HCN and 6H2O. And everything's in the gas phase, which would be important because if you're looking these up in these tables, phase matters. Okay, let's calculate the delta H. Again, you have to look things up to do this. I'm going to leave units off here because we know that the mole quantities are all going to be in moles and the enthalpies of formation are all going to be in kilojoules per mole. So when we multiply those together, it's always going to end up being kilojoules. Okay, so let's do HCN, 2 moles of that. The heat of formation for HCN is 135 kilojoules per mole. 6 moles of water, negative 241.8 kilojoules per mole for water. That's our products. We're going to subtract the same sum for reactants. We have 2 moles of ammonia, negative 45.9 kilojoules per mole is the heat of formation for ammonia. Oxygen, we have 3 moles of that, but it's an element in its standard state, so it really doesn't have a heat of formation. And then 2 moles of methane, negative 74.6 kilojoules per mole for that. Sum ends up being negative 940, and we know that that was going to come out in kilojoules. So that's using heats of formation and Hess's law together to predict the heat of reaction for a chemical reaction.